Okay, so today we're going to start with Chapter 5, and we're going to be estimating with finite sums. So let's take a look at just a simple example, distance traveled. So consider the following problem. A train moves along a track at a steady rate of 75 miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? So we know this goes back to Algebra 1, basically. Distance equals rate times time. So if we look at the rate, well, that's going to be 75 miles per hour. And the time, well, 7 to 9 a.m., that's a total of 2 hours. So when we apply that, our distance, so we have 75 miles per hour times 2 hours. Notice the hours will cancel, and we're left with 150 miles. Okay, so now we are going to make a connection between this formula and the graph of the velocity function. Okay, so one thing that we need to note is that this is a steady rate. So steady, and just another word for a constant. So it says this is the velocity, and it's going to be 75 miles per hour. So if we were to graph this, it would just be, here's 75, and it would just be a horizontal line. Again, just think of VFT, this is just like y equals 75. Now, we don't know where it's beginning and we don't know where it's ending. We just want to look at from 7 a.m. to 9 a.m. Okay, so if we were to kind of cut it off here, so we just want to look at 7 to 9, what we end up with is a rectangle. So we want to notice that the distance traveled by the train is exactly the area, the rectangle, whose base is the time interval from 7 to 9, and whose height, so there's the base, and the height is the velocity function, 75, right? If we look at this height is 75, this base is 2, multiply the area, and we get 150. So the whole point to this lesson is to consider a graph that's not necessarily constant, that perhaps it varies. So consider that the velocity function looks like that. And we'll say we still want to consider it from 7 to 9, but if we look at the area, it's no longer going to be a rectangle. So would the area of this irregular region still give the total distance traveled over the time interval? So in other words, when we did this example, we found that there was the connection between the area under the curve between 7 and 9, which ended up being a rectangle, and the total distance traveled. So would this area still give the total distance? And the answer is yes. So Newton and Leibniz thought it would. They imagined the time interval being partitioned, that's a key word, into tiny subintervals. So each one was so small that the velocity over it would essentially be constant. Geometrically, this is equivalent to slicing the irregular region into narrow strips, each of which would be nearly indistinguishable from a narrow rectangle. It'll kind of look like this. So we would have this shape. Here's 7 to 9. So imagine that we'd sliced it very, so that these were really narrow strips. So we could get a good approximation by looking at the area of these approximate rectangles. Okay, so the smaller the strips that we can get, the more accurate of the area under the curve, and therefore we could find the total distance traveled. And so we have a rectangular approximation method. So there are 3 different types of approximation methods. We have LRAM, which is your left-hand endpoint, your RRAM, which is right-hand endpoint, and MRAM, which is using the midpoints. So with all of these, we're basically looking at a bunch of rectangles. So if we have a curve, we want to use rectangles to approximate the area under the curve. The width of each rectangle is going to be the length of each subinterval, and the height is going to be the function's value at each endpoint. Now that's kind of hard to picture until we see our first example. So let's take it, look at the first example that we have here. So first of all, you have to notice that we have the curve is x squared. So obviously the curve that we're using will depend on what our rectangles will look like. And we have the interval is from 0 to 3, and we have 6 subintervals. Okay, so that's important also. So if we have 6 subintervals from 0 to 3, so imagine, obviously here we have 0, this is 1, this is 2, and this is 3. So this will be a half, this will be 3 halves, and this will be 5 halves. Okay. So the 6 subintervals, this tells us how many rectangles we have. So if I told you that there were going to be 8 subintervals, that means it would have 8 rectangles. Okay, so we are going to look first at LRAM, the left-hand rectangle approximation method. Okay, so basically what we're saying, and this gets a little tricky here, we're looking at this first rectangle. Now, looking at that really doesn't have any dimension, but I'm just going to go through the process so hopefully you can see it. So first of all, the left-hand endpoint, so it starts from 0 and it ends at a half. So the left-hand endpoint is the 0. The length of the subinterval, so if you just look at each of these subintervals, so the subinterval length is equal to a half here. Now, above, we just said the width is the length of each subinterval, and the height is going to be determined by the function's value at each endpoint. So if we think base times height, and so on, so I'm going to think of the 1/2 as my base. So I have 1/2. The height of this first rectangle, technically it doesn't have any dimension. The left-hand endpoint is a 0. So it's going to be base times height, 1/2 times 0. The next rectangle, okay, goes from 1/2 to 1. It still has a base of 1/2. The left-hand endpoint, so that's, we want to see for x squared where 1/2 is going to hit on the graph. So basically we want to plug 1/2 in for x squared. That's where we're getting that value. So technically the height of that rectangle would end up being 1/4. The next one goes from 1 to 3/2. Again, the base is still 1/2. They're all the same equal lengths. And we want to see, well, where does 1 hit on the curve here? So plug 1 into x squared, which will just be 1. So we know the height of this rectangle is going to be 1. The next one goes from 3/2 to 2. Again, its base is 1/2, and the height, so if we look at the left end point, which is at 3/2, we want to see where 3/2, the height of that rectangle is going to be 3/2 squared. Next one goes from 2 to 5/2. So the base is a length of 1/2, and then we want to plug in 2 to see the height of this rectangle. So that's going to be 2 squared. And finally, the last one goes from 5/2 to 3. Its base is 1/2, and the height is going to be determined where 5/2 hits on the curve. So that's going to be 5/2 squared. Now, we could double check, make sure that you have 1, 2, 3, 4, 5, 6 rectangles added together. So go ahead and take a minute to plug that in. You can see that we'll get 0 for this. So this will be 1/2 times 1/4, 1/2 times 1, 1/2 times 9/4, 1/2 times 4, and 1/2 times 25/4. So we have an 1/8 plus a 1/2 plus 9/8 plus 2 plus 25/8. Okay, so you should get 6.875. Next, our RAM. So we're going to repeat the same process for the right-hand endpoints. So in other words, if you look at each subinterval and you look at where the right endpoint will reach on the graph. So again, we have 0, here's 1/2, here's 1, 3/2, 2, 5/2, and 3. Okay, so for each of these, the base are still going to be 1/2. So if you want, you can actually take the 1/2 all the way out to the front and just multiply it. But just for right now, I'm going to leave the 1/2 as our base and the height. So now let's look at the first interval. The first interval goes from 0 to 1/2, but we don't want to use 0. That's the left end point. We want to use the 1/2. So it's going to be 1/2 squared, because that will be the height of that rectangle. Next, we have 1/2 to 1. So we want to look at the right-hand endpoint. So that's going to be 1 squared. And then we go from 1 to 3/2. So 3/2 is going to reach on the curve, and that's going to determine the height of that rectangle. Then it goes from 3/2 to 2, so we look at where 2 hits on the graph. So that's going to determine the height of the next rectangle. 2 to 5/2. 5/2 is the right endpoint. So that would be this rectangle. And finally, the last one goes from 5/2 to 3. So 3 is going to determine the height of that rectangle. So if you look closely, LRAM and RRAM are pretty much the same, except the first one and the last one. Okay, so basically RRAM skips the first rectangle that we had in LRAM, And LRAM skips the last one that we had for RRAM. Go ahead and add that all up, and that you can, just plug that right into your calculator. Just remember, for these, I'm always going to ask that you round to 3 decimal places, and that's fine. So go ahead and take a minute to add that. Now, when you're looking at these numbers, 6.875, notice there was all this empty space, in between the rectangles and the graph. So this was an under approximation for the area under the curve. Whereas RRAM, all the rectangles went above, and so the rectangles take up too much space. So you can kind of guess with midpoint, that's going to give us a more exact solution here, because you'll see some of the rectangles, some of their parts go above, some go below. Now, midpoint rectangular approximation method. Again, we still have 1/2 for all of our bases. But this one gets complicated because we don't want to use the 0, the 1/2, the 1, the 3/2, the 2, so on. We want to use the midpoints of those. So basically the midpoint of 0 and 1/2 is 1/4. So we're looking at the midpoints of these. So as I was just saying, the midpoint of the first subinterval, so from 0 to 1/2 is going to be 1/4. And then from 1/2 to 1 is going to be 3/4. So right here is 3/4. And then here, this is going to be 5/4. And then this is 7/4. This is 9/4. And this is 11/4. So those are all of these are the midpoints of each subinterval. So they are going to determine the height of the rectangles that we see here. So if you kind of look at, notice where it hits right in the middle of each rectangle. So the first one's going to be 1/2 times 1/4 squared. The next one's going to be 1/2 times 3/4 squared, 1/2 times 5/4 squared, 1/2 times 7/4 squared, 1/2 times 9/4 squared, and 1/2 times 11/4 squared. So go ahead and take a minute to plug that into your calculator. We should get 8.9375. So let's take a look at example 2. We want to refer to the region R enclosed between the graph of the function, between the graph of the function y equals 1/2 x squared and the x-axis from 0 to 4. So first thing we want to do is graph it. So let's start from 0. If we plug 0 in, we get 0. If we plug 1 in, we get 1/2. If we plug in 2, well, 2 squared is 4 times 1/2 is 2. And plug in 3, so 3 squared is 9, divided by 2 is 4.5. And 4, plug in 4, we get 4 squared is 16 times 1/2 is 8. So here is the graph that we're looking at. So we want to kind of cut it off. That's the region R that we are looking at. So we're going to partition R into 4 subintervals. It's nice because it's 1, 2, 3, and 4. No, don't have to worry about decimals in this first example, or this example here. And we want to do LRAM. So again, since the base is 1, and we're doing base times height for each of these, we really just need to look at the height, right? So for example, the first rectangle for LRAM would be here. And again, we have the same situation as we had on the previous page, in that the base is 1, the height is 0. Because again, go back to 1/2 x squared, and that's going to help you to determine the height. So if I plug in 0 for 1/2 x squared, I get 0. The next rectangle goes from 1 to 2. So my left end point is 1. So we pictured that's our rectangle. So if I plug in 1 for x squared, I get 1/2. Next goes from 2 to 3. So I look at where 2 hits on the x-axis, and that's going to be at 2, so that's the height. Next one, oh, and I didn't draw, there's my rectangle. Next one is 3, and that is going to be, so 3 squared is 9 times 1/2 is 9/2. So plug that into your calculator, and we should get 7. Now we're going to repeat this. So for C, we're going to repeat this process, but for RRAM. So I'm just going to kind of erase the rectangles because our rectangles change with RRAM. So the first one is going to go from 0 to 1. So here's our rectangle. So RRAM is going to be 1 times 1/2. Basically, it's going to look like this one above, except for it's going to have one more in the end. So again, if we go from 1 to 2, 2's the right hand. So it's going to be 1, and then plug in 2, and we get 2. Next one goes from 2 to 3. So 3 determines the height of the rectangle, and we said that was going to give us 9/2. And finally we have one more rectangle. This one goes from 3 to 4. So 4 determines the rectangle's height, and that gives us 8. So we have 15. And finally we have MRAM. So again, if I just kind of go back here and consider now, I don't want to use the 0 or the 1, the 2, the 3, the 4. I want to use the 1/2, the 3/2, the 5/2, the 7/2. So each of these 1, 2, 3, 4 values will get plugged into the y equals 1/2 x squared, and that determines the height of these rectangles. Okay, and so on. So MRAM, and base hasn't changed. Base is going to stay the same for all of these. So it's going to be 1. Now when I plug in 1/2, so it's like 1/2 times 1/2 squared. Next one is 3/2, so it's going to be 1/2 times 3/2 squared. Next one is 5/2 squared. And finally the last one, 1 times 1/2 times 7/2 squared. So plug that all into your calculator. And on Monday I will show you, there's a calculator program that you can use to check your answers. So when we get to that point, I will show you. We should get 10.5 here. Okay, our last example for today is you're given a table of values, and they show the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled, okay? So we're going to use 10 subintervals of length 1 with LRAM and RRAM. So when you have a table of values, we think of these, so like it'll go from 0 to 1, and then you have to determine, so like if it's the left-hand endpoint versus the right-hand endpoint, which one you're going to use. So as we saw in these previous ones, okay, so like if we compare the last example, B and C, we used the first one but not the last one. Like we used the 0 but not the 4. And with RRAM, we didn't use the 0, but we used the 4. So the same thing is going to be true for these. Now, subintervals with equal length. Okay, so we can see that the time interval, the base, is going to be 1 because it just keeps going up by 1 second. And the height, well, the height's going to be determined by the velocity. Okay, so if we look at these last columns. So for LRAM, I'm just going to put the 1 out in front just so you remember, because it's going to be base times height plus base times height plus base times height. Okay, so we are going to use the 0. We're going to use the 12, 22, 10, the 5, the 13, 11, 6, plus 2, plus 6. I'm going to stop there. I'm not going to use this 0 with the left-hand approximation method, just like when we were using the graph. So you're basically just adding up all those numbers. So we have 12, 22, 10, 5, 13, 11, 6 plus 2 plus 6. We get 87. Now for B, for RRAM, it's going to be 1. We're not going to use the first 0, so we're basically skipping the first one. So we're going to start with 12. And we are going to go through. Now this isn't always going to be the case, but you may have noticed that the last one has a velocity of 0. So if in LRAM the first one was 0, and in RRAM the last one was 0, we should end up with the exact same results. Okay, so for tonight you're going to work on the worksheet on rectangular approximation method. It's assignment number 32, and I will post solutions to those. So hopefully you can complete the assignment, and then we will move on and do the next lesson.